So the first time I made this video, I did it, polished the example, and then realized as I went to go do the video editing, I'd used the wrong word and used it over and over and over to the point I had to remake this video. So this is the third time I've had to make this video now, because the second time I started doing it and then realized I'd named the compound wrong. So we're going to talk about allylic, not aliphatic, allylic hydrogens with regards to these two compounds. Here we have 2-methylpentane, and here we have 4-methyl-1-pentene. Now, both cases we're going to react these with Cl2 and light. And the question is, where does the Cl end up, assuming we only have one chlorine added? Now, from your memories of alkanes and reactions of alkanes, you should know that for this compound we're going to attach the chlorine here. Well, with this compound down here, there's actually two places we can attach the chlorine with preference given to one of them. Two places will be here and here, with this being the majority. So what's the difference between these two compounds? Why does one pretty much give exclusively this product and the other one give it here on a secondary, not a tertiary, and even some on the primary? Well, the answer here is that this is what makes allylic carbons unique. An allylic carbon is one that is adjacent to a carbon-carbon double bond. And because they are adjacent, they can participate in resonance. Now, the reason why this reacts first is that we know that a tertiary radical is more stable than a primary and secondary radicals. So if we were to create a radical on this carbon, it would be less stable than the tertiary. But here, if we create a radical, which is what occurs with this type of reaction, resonance will let us bounce back and forth to give this species. Now, this is a secondary and this is a primary. None of these are as stable as a tertiary radical on their own. But anytime you start invoking resonance, you start increasing stability. So even though each of these individual radicals are not more stable than a tertiary, combined with the resonance structures, they are. And because we have resonance, we have the option of reacting here or here. Now, the secondary radical is going to be more stable than the primary, which is why our majority product is going to be this, but we're still going to acquire some minority product that looks like this. Now, why is this relevant? Well, as we start working with aromatic systems, particularly when we can do resonance with aromatic systems, we get far better reactions on those allylic carbons than we ever would on anything else on an alkane backbone. So this is something to keep in mind when you're working with aromatic compounds and dienes, trienes, and all these, enes in terms of chemistry. It's no longer what you were dealing with simple chemistry when you were working with alkanes. You have to consider possible resonance structures. Anytime you have a double bond, consider what happens in the reaction in terms of stabilizing any types of intermediates that are formed. If we can do a reaction where a carbocation or a radical is created on the allylic carbon relative to a double bond, we are more likely to have the reaction occur there than anywhere else in the molecule.